concluding speaker from the Ventspils International Radio Astronomical Center, so Artūrs Vrubļevskis, and he will be also the final speaker for this session today.
Okay, well, good afternoon to everyone. My name is Artūrs Vrubļevskis, and I'm part of the Solar Research Group here at VIRAC. And today I would like to talk about the investigations that we have performed for sunspots as sources of slow solar wind. So the open question that we try to address is the slow solar wind sources. So as some of you may know, solar wind is in general broadly differentiated into two categories: fast wind, which is known to originate from polar coronal holes, and the slow wind, which is slower, as the name suggests, but also has other properties that differentiate it from the fast wind. But the interesting thing is that the source of the slow solar wind is unknown. And so it could be the boundaries of these coronal holes where the fast wind emanates. So on the boundaries, maybe you would have the slow solar wind. Maybe it is the helmet streamers. Maybe it's the pseudo streamers. Maybe it is blobs connecting from the helmet streamer cusps. Maybe it's what is called equatorial coronal holes, which would maybe sometimes are related to edges of active regions. And so the sources are unknown, and it is a lack of basic understanding, and knowing more about these sources would then trickle down and influence other solar physics research. So while this is not directly related to the title of this workshop, the flares and superflares, I believe that we do need to have the knowledge or understanding of this fundamental question in order to do better with flare and CME predictions. So we would like to provide the understanding of the ambient solar wind. And as you will see, as we're attacking this question, we're also getting understanding of the magnetic fields of active regions, of the atmospheres of active regions. So I believe that could also add to the understanding of these impulsive activity events, because you have the background understanding of the atmospheres and the magnetic fields, which you can then feed into your models and trying to understand the starting point or the equilibrium starting point of any activity that you would like to model. So previously, we're working under the hypothesis developed by the leader of our research group, Boris Ryabov, who observed and noticed that some sunspots display a dark region in EUV and in X-rays. You can see these dark lanes. And his hypothesis is that maybe there are open field lines at these locations, and then outflows along these open field lines could maybe be one of the sources of slow solar wind. And this is particular one sunspot, 8535, that we have been investigating extensively. So like I said, this idea goes back with Boris already several years. There have been previous papers published, and now the latest ones from 2020 and 2021 are the ones that I would like to talk about in this talk. So the first one is mainly focused on the coronal field structures for the sunspot. And then in the second one, we talked about the microwave observations and how those are related to the atmosphere, solar atmosphere above this sunspot. So in the first paper, Boris and I, we looked at the open field structures and did PFSS magnetic field modeling, and discovered that there's what we would call a funnel. So open field lines emanating from a rather small foot point on the surface of the sun, and then expanding broadly into the corona. And then these corridors, and which also consist of open field lines and a separating surface in between. So in the paper, we did try to relate these open field structures to other observations to see the effects of that. and related also to the in situ observations by ACE spacecraft at 1 AU, where we could identify the slow solar wind and relate it to tentatively this active region. The radio observations were performed by the Very Large Array in the United States, the VLA, and these are the observations that I used in my research for the analysis. So the same sunspot, the contours of the umbra and penumbra are shown here in white, was observed in 3 frequencies, 5, 8, and 15 gigahertz, and in 2 polarizations. And in this case, the right circular polarization would correspond to the X mode, and left circular polarization would correspond to the O mode. And if we look at these observations, the distinct feature that we would like to understand is this region of reduced microwave brightness temperature in the northern part of the sunspot. So why is it there? What are the causes of it? So these observations are from 1999, and already in 2004, these observations were described in a paper by Brosius and White, and for the same sunspot. And there they talk or conclude that there is what they call a plume in this northern part, where you have plasma of lower temperature. And they related these radio observations to observations of, in this case, oxygen 5 line, which is, when we're looking at the colors, is bright at these very same points where you have this reduced microwave brightness. So it suggests that you have this lower temperature plasma at this location. And in our research, we would like to relate or maybe explain this plume better by relating it to open field lines. So our claim would be that it's not simply like a blob of plasma there, but it's actually plasma along open field lines. And the reason for this lower temperature is related to the open field as opposed to closed field. So we used magnetic field observations from SOHO. So here in the center, we have the surface magnetic field. And in the EIT observations, you again see these dark lanes. And then we use the magnetic field measurements to construct the magnetic field model for this sunspot. And if you do that, you do find the open field lines that you already talked about in the first paper. Here I'm showing that the magnetic field is actually, how to say, regular. So there are no distinct features. It's the sunspot, the magnetic field is pretty much circular. So there is nothing specific in this northern part where you have the reduced microwave brightness temperature. So in terms of magnetic field strength and direction, there's nothing distinctive there. But if you do a global trace of field lines, then we find open field lines along a volume in the northern part of the sunspot. And this box represents the model volume where that we set up, where we would set temperature and density in the atmosphere. And we would have 2 parts or 2 components for the atmosphere. One in the volume occupied by the open field lines, and another one for the bulk or the remaining volume. The interesting feature immediately is that these open field lines occupy a region that is co-located with this area of reduced microwave brightness. So like I said, we set 2 different parameters, 2 different atmospheres, parameterize 2 different atmospheres using a model described by Alessandrakis, Kundu, and Lantos, where you have parameters that you can vary, the height where you have the transition layer, the starting density, and the conductive flux. And so I would vary those parameters for the 2 components until I get the best match with the observations. And here and on the right, I'm showing the profiles at a cross section of this sunspot. So for temperature, you see that you have the hot bulk component, like your regular atmosphere, going up to several million degrees, and the cold plasma along the open field lines. In terms of density, I'm forced to, or my model finds that the density is increased along open field lines in the lower atmosphere and then rapidly decreases with respect to the surrounding bulk atmosphere. So this is what we get for the, in our model for the brightness of our sunspot, and we get the expected, or what we're going for, the reduced brightness temperature in the northern part of the sunspot. But this is before the smoothing. So when we take into account that the radio telescopes have finite resolution, then we smooth out the data for better comparison, and then this reduced brightness area becomes significantly less distinct. So then we can compare visually to the observations. Initially, it seems that the differences are very unnoticeable, but a couple of points. First, I model, or I do the comparison only along this cross section, because these bright areas, for example, which are very distinct, for example, in 8 gigahertz, these red spots, those are actually extremely unusual. And it seems that there is some sort of heating happening in higher layers, in lower layers compared to higher layers of atmosphere. So these bright spots are beyond what we could model. So I was actually going for a model for the regular part of the sunspot. So that's why I picked this cross section. So the lower part should correspond to what you would expect in a regular sunspot. And then the northern part would correspond to this area that we are struggling to explain. So the idea is that we don't have to look at these bright spots, but only at this cross section. And the other point is, like I said, is that it seems that this reduced brightness temperature area is smoothed out. Recently, I ran improved model of the magnetic field for the same sunspot, and it seems that this volume that I previously showed is actually broader in an improved model. So that would also mean that this that the area of reduced brightness temperature is also broader, and that would probably lead to a better match with the observations. So if we look not at the image, but the actual cross section, you can see that, and then so for these cross sections, the dotted line is what you would have with only the bulk atmosphere, and then the dashed line is what you get with this additional component of cold atmosphere along the open field lines, and the solid line is what you have observed. And we can see, for example, in the 8 gigahertz, the match is actually really good. We also reproduce this increase in 15 gigahertz. It seems that despite using this cross section, there's influence from these bright area, and which I have not completely avoided with my chosen cross section direction. So that's the main science results, and the main conclusions would be that we manage in our model to reproduce this reduced brightness temperature in another part of the sunspot, and it seems that at least for this sunspot, we can this sunspot plume also interpret as low temperature plasma lying along open field lines. And we used, in this case, the complementary multi-messenger data, so both radio, EUV, and in situ observations. So for future, we would like to investigate other such sunspots. We would like to use EUV and X-ray observations, not just to see that there are dark lanes, but to use them to get additional measurements of plasma density, temperature, or Doppler shifts to actually see the outflows. I have already started working on elaborating the magnetic field model to improve it. And these days, use the Parker Solar Probe and Solar Orbiter for in situ observations of the sunspot and the emanating, allegedly slow solar wind. And in the future, even better measurements should become available from the frequency agile solar radio telescope that is being proposed, which would have a broad range of frequencies and high spatial resolution to get even better pictures than from VLA. So that's in short what I had prepared in terms of the science that we have done and plan to do in the future. So I think I'll stop here.
Okay, thank you a lot for an interesting talk, and also thank you for keeping the time. it is indeed always very impressive when you have such a decent agreement between observations and theoretical modeling. So I could possibly begin with my own question. You showed the synthesized images of the microwave emission, right? So what software, what methodology did you use to produce these microwave images from model?
It's emission from gyro resonance layers, and it is free Bremsstrahlung emission. So the formulas are there's nothing too complex in it. The actual implementation, as described in the paper, we used, I based it on what is available in Solar software in one of the packages. It's escaping my mind right now, but it's I just used it from and slightly modified for my own need. So in terms of the microwave calculations, it's the most basic formulas and nothing fancy there.
Yeah, I see. Okay, thank you very much. So I think Krishna was next. So Krishna, please unmute yourself and speak up.
Yes. Hi. So I was wondering, these dark regions are related to active region fan loops, which are at the edges of the active regions. So if they are generally rooted in the umbra of the spot, which also in your plots somewhat looks like it is rooted in the umbra. But I mean, these are long, these are very long loops in terms of EUV loops, which you see. These are very long range loops. But however, something that is rooted in the umbra of the sunspot, how can they be open structures in terms of solar wind, not in terms of the length of the loop itself?
Yes, so that's a question that's been that's important to us and has been asked also, was asked by the referee of our paper. So how do you distinguish between closed loops with cold plasma from open loops? And
Krishna, I suppose you uncovered yourself now.
So
no, I'm not the referee.
So in one of the future directions, which I have not listed here, is indeed doing better job and in distinguishing where we have these closed loops with cold plasma. And thus another reason why maybe our model produces narrower region is because maybe in reality next to this cold plasma you have loops with cold plasma, which in our model are not reproduced. Second part, yes, I'm aware of this idea of loops emanating from umbra, of these fan loops emanating from umbra, but I personally don't really agree with this viewpoint that somehow umbra, the location umbra penumbra is important. I think that the main question is, are these loops closed or open, irrespective of where they start from? And so I don't really myself see the reason why, say, a loop that starts here in the umbra, if it goes high enough, whether it is open or closed is determined by the global magnetic field. Far away, comparatively high above the sunspot, the global field will determine whether the field line is open or closed. So if it goes high enough, whether it loops back or it goes into the interplanetary space. So I personally would stray away from this paradigm of looking umbra penumbra and just with an open mind look for closed or open field lines.
Yeah, but I mean, like you mentioned, from the umbra, if there is any field to have connectivity between the 2 foot points of the sunspot, for example, the two foot points of the active region, if there is any field that is connecting to the other foot point, that should be the strongest of the field from the umbra, right? Rather than, so if that is connecting to the other foot point, then somehow it is irrelevant to the solar wind perspective openness of it, right? No?
Yes, so yeah, so you would have to look at the particular geometry of your sunspot and see where you can find the open field lines. So our sunspot is, so if you look, I see if I have a good picture. So our sunspot is, I I guess it's called the alpha type. So it's somewhat isolated, and you don't have a distinct opposite polarity surrounding it, or in other words, it's in many directions. So it looks like a dipole, which is directly radial instead of the bipolar, instead of a clearly bipolar sunspot. So in this case, the open field lines, if they exist, would indeed be right above the sunspot. If you had a bipolar field, then yes, you would have a closed field lines going from one end to the other, from one polarity to the other, and then you would have to look at the edges of the active region to find open field lines. So I guess it all depends on the magnetic field configuration, and indeed, for a bipolar magnetic field, for a clearly bipolar sunspot, you would have to probably look at the edges of the active region to find the open field lines.
Okay, thank you very much.
All right, thank you. So we have one more question from Val. Val, please.
Okay, so thank you, very interesting. Any ideas why so the plasma is cooler in this plume? So in other words, what does suppress the coronal heating mechanism operating everywhere in the corona, because the corona is actually more or less uniformly hot, meaning it is heated continuously and everywhere, but somehow in this, say, narrow plume, so the heating mechanism fails. So any ideas why?
I'm hesitant to talk about this. It's not really my specialty yet, and I'm still learning more about it. An immediate guess would be that you have the hot plasma streaming away and leaving the cold plasma behind. So that would maybe be one option.
Excuse me, do you mean it's like a vacuum cleaner mechanism? So meaning somehow so the cold material from the chromosphere is sucked by the, well, possibly the, so pressure gradient, and so what we see actually is the chromospheric material, so which goes up, right?
I don't think you necessarily need to have chromospheric material, just that of all the material, the hot one manages to escape, leaving the cold one behind. That would be an uneducated immediate guess. But yes,
no, it's not the cold plasma left behind. It's like in the coronal holes, the heating might be the same, but then some of the energy is taken away by the acceleration of the plasma itself, and only some of the energy is left for the heating. So that's why it is cold, just like in the open field lines in the coronal holes, right?
No, coronal holes are not very much, say, cooler than, say, active regions. So we are talking about just a few times, not an order of magnitude. So in the, well, in coronal holes, the temperature is also 1 million Kelvin, maybe just slightly lower.
Okay, I should also clarify here.
And also, excuse me, I just add to my answer to this point. Also, so if it's say an empty, if it's a void in this case, so the mass of the plasma is also lower, and so there is no need for a lot of energy to heat it. So there is another issue. It's not just deficit of energy, it's also decreasing the mass, meaning so the total amount of energy required to heat it up to 1 million Kelvin is also low. It's the trivial, I think, point.
But I should note that maybe I've been in this quick presentation didn't stress enough, or actually didn't explain the part where we're using microwave emission, and it mostly comes from the gyro resonance layers, which I've shown here in black. So in reality, I'm constraining the model and the atmosphere pretty much only at the heights of these gyro resonance layers. So with some, the real conclusions that I can make are only about the plasma up to these and including these heights. So in most likeliness, in larger heights, the plasma does get heated and the density is different. So in reality, what I have really diagnosed are these lower heights, not what is going on higher above. So the idea was to use this model, and it is parametrized, and I didn't go beyond into different models, but in future research, we should probably use different profile for these open field lines, where indeed we would manage to get both the cold and dense plasma in the lower heights, and then still allow for heating and an increase in temperature at larger heights.
But
So guys,
by thermal conduction.
So sorry guys, so I suggest us to move this discussion to 40 minutes reserved specifically for discussion and conclusions in the end of the workshop. So after the end of the second session. So with this, I would like to thank Artūr again and all the speakers of today's session, of the first session, one more time. So thank you very much. It was very interesting and instructive.